Welcome to the video on a math topic called variation. Here's the general idea. Scientists and mathematicians study relationships between two variables all the time. Let's call those variables x and y. They might represent something in real life, but we'll talk about them in more generalities here. And quite often, mathematicians and scientists discover that as one variable increases, so does the other. You can see by this drawing that as x increases, y is also increasing. We call that a direct relationship. For example, one could surmise that as study time increases, GPA increases. In this particular graph anyways. So study time and GPA are said to have a direct relationship with each other. But sometimes mathematicians and scientists notice that as one variable increases, the other one decreases. You can see in this drawing that as x increases, y decreases. We call that an indirect relationship. There are many examples in real life of indirect relationships. One might be your weight and your average speed. As your weight increases, we might expect speed to decrease. But let's change the discussion to a very special kind of direct relationship. There are many direct relationships, but there's a certain kind that is represented by a straight line emanating from the origin. When we have this kind of direct relationship, we don't just call it a direct relationship. It's also known as a direct variation between the variables. I'll give you an example of some characteristics of direct variation. Suppose that at one point on your curve, or line in this case, you had an x value of 3 and a y value of 7. It's an interesting question to ask. What would happen if the x value were to double from 3 to 6? Well, there'd be a corresponding point on the graph, and perhaps it's no surprise to you that the y value would also double from its original value of 7. And this isn't only true for doubling, it's true for any kind of increase. If x were to triple, y would triple, and so on. If x were to go up by a factor of 2.4, y would go up by a factor of 2.4. And when we have this kind of relationship, this direct variation between the variables, the equation is expressible as y equals number times x. That number will vary from situation to situation, but the equation will always be expressible that way. When this situation arises, we use the phrase y varies directly as x. We also say y is directly proportional to x. Sometimes we leave out the word directly and just say y is proportional to x, with the directly being understood, as this is one of the most common kinds of proportionalities or variations. Let's change our focus now and look at a very special kind of indirect relationship. In general, an indirect relationship is one in which when x increases, y decreases. But more specifically, we could have a curve that describes the relationship between x and y that looks like this. We have this kind of curve, and I'll be more specific about this in a minute, but when we have this kind of indirect relationship, we not only call it an indirect relationship, but we call it indirect variation. But it has to be more than just the curve that looks like that. It has to have the following characteristic. Follow me on this idea. Suppose we had a point on our curve that had a particular x value, say of 2, and a y value of 20. What if x were to go from 2 to 8, essentially to quadruple in size. So if x were to quadruple or increase by a factor of 4, 8 is 4 times as big as 2, we would expect in an indirect variation relationship, we would expect that y would decrease, but not just to any number. It would have to decrease to 1/4 of its original size when x was 2. So to repeat that, if x increases fourfold from 2 to 8, y would decrease to 1/4 of its original size, or 1/4 of 20 is 5. And when this kind of proportional indirect relationship exists, we call it indirect variation. In these situations, the equation is always expressible as y equals number divided by x, and we use the phrase y varies indirectly as x to describe this kind of relationship. We also say y is inversely proportional to x. Now let's take a look at our first example, and we'll look at an example of a direct variation problem. Suppose we have two variables, x and y, and suppose there's a direct variation between them. Further suppose that when x is 4, y is 5. And we want to find the value of y when x is 6. Before we start this problem, if you're wondering how x can be 4 and 6 in the same problem, it's because we're thinking about x and y as true variables. There's some moment when x is 4, and later on it's 6. Okay. Because we know and been told that y varies directly as x, we know that the equation between y and x has to be this format, y equals some number times x. It's not traditional in math to use the number sign to solve these problems, so we'll use the letter k instead. It doesn't matter what letter we use there, I just don't want to use the number sign. Traditionally we use k and it represents something called the constant of variation. But aside from what it's called, let's do the math. We know that when x is 4, y is 5. That means this equation must be satisfied when x is 4 and y is 5. And therefore I can plug in 4 and 5. But this is very helpful because this is going to allow me to solve for k, the constant of variation. All I have to do is divide both sides by 4, and I now know the value of k. By the way, 5 divided by 4 as a decimal is 1.25. It's not typical to use decimals in an algebra class, so I won't. But now that I know that k is 5/4, I can take my original equation and replace k with 5/4, as would be fitting here. But now that I know the constant of variation, I can go on to answer the question. The question was, notice at the top of the screen, to find the value of y when x is 6. Well, if I know that this equation at the bottom of the screen is the relationship, and I know that x is 6, I can plug that in to find out what y is. Just a reminder about a fraction times a whole number. Notice at the bottom of your screen, when you do a fraction times a whole number, the whole number only multiplies by the top of the fraction. 6 times 5 is 30. Notice I didn't change the 4. Furthermore, 30/4 is reducible. 30/4 reduces to 15/2. Now 15 divided by 2 in decimal form is 7.5, but again, it's not traditional to use decimals in an algebra class, so I would typically leave my answer as 15/2. Now while I am done with this problem, the answer is 15/2, or 15/2. There's something I'd like to add that you might find helpful, or you might not. See if your brain works this way. Some students can do this entire problem without the algebra, in some cases. See if you're such a student by following this logic. Notice at the top of the screen, x started out being 4, and later increased to 6. How much did x increase by? Well, some people would say it increased by 2. Well, it did. But for direct variation, we're not interested in how much it increased by. We're interested in by what factor did it increase. When x went from 4 to 6, it increased by a factor of 1.5. It's now 1.5 times its original size. If this is not the way that your brain works, then don't use this method, whatever you do. But if you do understand that x increased by a factor of 1.5, then it's safe to assume that y would also increase by a factor of 1.5. That's the very definition of direct variation. And so 1.5 times 5 would be 7.5, or 15 halves. Again, depending on the way you think, this may make absolutely no sense to you, or it may make brilliant sense. If it doesn't make any sense, just use the algebra and don't think about it in terms of factors of increase. Let's now take a look at an inverse variation problem. Suppose again we have two variables, but this time y and x vary inversely from one another. Suppose further that when x is 8, y is 3, and we want to find the value of y when x is 4. So because the variables have an inverse variation or are inversely proportional to each other, we know that the equation that represents them has to be of the form y equals some number over x. We don't yet know what that number is, but we know the equation has to have that format. Now, instead of using the number sign, we'll once again use the letter k as our constant of variation. You're not obligated to use the letter k. You can use any letter you want whatsoever. Now, we also know that when x is 8, y is 3. That means this equation has to be true when x is 8 and y is 3. And therefore I can plug in x is 8 and y is 3. Now, I can use this to solve for k, my constant of variation. All I have to do is multiply both sides of the equation by 8, and that tells me that k is 24. It's essentially a cross multiplication. And now that I know that the constant of variation for this particular problem is 24, I can plug 24 into my original inverse variation equation. Now that I've found k and have my new modified equation, I can answer the question. Notice at the top of the screen you're being asked to find the value of y when x is 4. Well, since this equation must always be satisfied in this situation, I can simply plug in 4 for x and work out y as 6, which came from 24 divided by 4, of course. Now I'm done with this problem, but let me once again share a thought process with you that you might find helpful. Occasionally, when the numbers work out, there's a way to do these problems without algebra. You may or may not think this way. Watch and see if you do. Notice at the top of your screen, in this problem, x was 8 originally and became 4. So it went down. How much did it go down by? Well, you might say it went down by 4, and you wouldn't be wrong, but we're not interested in how much it decreased by. We're interested in by what factor it decreased. And if x went from 8 to 4, it decreased by a factor of 2. That's another way of saying it's now half the size it used to be. But there's an inverse relationship here between x and y. So as x decreases, by a factor of 2 in this case, y has to increase. And therefore it must go from 3 to 6. Because as x decreases by a factor of 2, in other words, gets cut in half, y must increase by a factor of 2, in other words, double. So is the nature, by very definition, of an inverse relationship. If you don't think that way, don't think that way. Simply do the algebra and you'll arrive at the same result. And finally, let's take a look at a problem that not only involves a mixture of variation between several variables, some direct, some indirect variation, but we'll also look at a scientific example here. Before we do, I need to take you on a little mental journey. I'm going to ask you a seemingly silly question here. What's brighter, a flashlight or the sun? Well, obviously the sun is, but in science there is a measure of brightness that takes the observer into account. For example, that flashlight is a lot brighter than when it's 6 inches away from your eye than the sun would be if you were standing on Pluto. And so this notion that we'll need to keep in mind for this problem is that brightness depends on where the observer is in relation to the light, and as well as the power of the light source. Clearly, the sun is more powerful than a flashlight, but if you were far enough away from it, the flashlight could be brighter than the sun. Anyways, here's the actual problem. So the brightness of light, which we'll call B, is proportional to the power of the source and inversely proportional to the square of the distance from the observer, how far the person is from the light. This is a scientific fact. Now, suppose for a particular light, it had a brightness of 54. Now, I won't attach any units here because I don't want this to become too much of a science-based problem. But just say there's some brightness scale and this light has a brightness of 54 when the power is turned to 15 watts and it's 2 meters away from the observer. Now suppose that same light is then raised in power to 30 watts, but it's moved further away. It's now 6 meters away from the observer. And we want to find the brightness of the light now compared to where the observer is relative to its old position. Okay, this is a very complicated problem, but it is a variation problem, and it can be solved using the tools that we saw on the previous two simple examples. One very important math skill is the ability to see what's important in the problem. And so I've changed some things here to be visible in color so we can focus on them. It's not showing up on your end. Apologize for that. Now, what I'm going to do is I'm going to take this scientific fact and make an equation out of it. Well, this is the equation that we would make out of it. Let me explain. K represents the constant of proportionality. And because the power of the light source is directly proportional, it doesn't say directly there, but that's the assumption when we say proportional. Because the brightness of the light is directly proportional to the power source, then the power variable goes in the numerator. And that's where we put our quantities for which there's a direct relation. And because the brightness is inversely proportional to the square of the distance, d squared, then d squared goes into the denominator. So any variable that's directly proportional or varies directly in the problem goes in the numerator, and any variable that has an inverse or indirect proportionality or variation goes in the denominator. The k, you could actually put in the denominator or the numerator, and it wouldn't matter in this problem, but I'll put it in the numerator for simplicity. So now I've converted my scientific fact into an equation. I'm now going to move on to the data that I have about this particular light. And my goal here is if I can plug that data into my equation, I'll be able to solve for the constant k. And I've plugged in my information from the problem here into my equation. If you need to pause to look back and forth and convince yourself, I recommend doing that. Now at this point, I used scratch paper to solve for k. And I got that K is equal to 14.4. Now, just to show you the algebra, here it is. If you'd like to hit pause and analyze the algebra here, it might not be a bad idea. Now, I don't ordinarily like decimal values, but I have a tendency to use decimal values whenever I'm solving a scientific problem, as opposed to a purely mathematical problem. So I'm going to break with my normal no decimal tradition here and express K as 14.4. But now that I know that K is 14.4, I can modify my equation by plugging in 14.4 for K. Well, so far that's all I know. But now let's move on to the question. So this light has now a higher power, but it's further away. Which do you think will impact the brightness more? The fact that we doubled the wattage, the power, or the fact that it's now 6 meters instead of 2, or tripled the distance that it used to be? Clearly, cranking up the power to 30 watts will make it brighter, but then moving it further away will make it appear less bright to the observer. And it's an interesting thought to ponder, which one of these will have a larger impact on the ultimate brightness. In other words, will it be higher than 54, which it was before we moved it and turned it up, or will it be lower? Well, the algebra will tell us. So what I'm going to do here is plug in the new information about the light now that it's moved and turned up in power. I'm plugging in the 30 watts and the 6 meters. And you can calculate these by hand or on a calculator, depending on if you're a class that allows calculators. Either which way, it didn't show my scratch work here, but either which way, the brightness of the light turns out to be 12, whereas it used to be 54. So we can see that the brightness has gone down quite a bit here from what it used to be. The final answer to this problem is that the brightness is 12 on whatever brightness scale we're using. And while I am done with the problem, I'd like to point out once again that the algebra could have been avoided completely here if your brain is willing and able to sort of stretch itself in the following way. See if you can follow this alternative solution. Here goes. Originally, the wattage or power of the light was 15, but we doubled that to 30. And because we doubled the power, we're going to double the brightness to the observer. But at the same time, we moved it further away. It used to be 2 meters away, and now it's 6 meters away. Now, that has increased by a factor of 3. It is now 3 times as far away from the observer as it used to be. But further away means less brightness. And because of the square of the distance, or the d squared, whenever you triple the distance, you will decrease the brightness by a factor of 3 squared, or 9 in this case. Let me repeat that. We've tripled the distance away. The brightness is inversely proportional to the square of the distance. 3 squared is 9, so our light will diminish in brightness by a factor of 9, or be 1/9 of what it used to be. Well, both of these will have an effect at the same time. It will double and then decrease to 1/9 of its original size. The net effect then is that this 54, this original brightness, will decrease by a factor of 2/9. In other words, it will be 2/9 of what it used to be. If you work this out on a calculator or on paper, you will in fact get 12. Now, if you're inclined to think that way, you're a very lucky person. A typical student doesn't think that way. And so most students tend to rely on the algebra rather than that kind of thinking. But they're both correct, and you can use either one that is suitable to your own learning. And that completes the lesson on variation.